Hello everybody and welcome to our new video training package of Abacus. Composite pressure vessel analysis with semi-geodesic winding. Looking to learn more about pressure vessel manufacturing methods? Check out our new package. In this video, we introduce you to the package that explains the intricacies of pressure vessel simulation with the semi-geodesic filament winding method using Python code. We'll also show you how the package examines damage using UMAT code, giving you a comprehensive understanding of the entire process. Whether you're an engineer or just curious about the topic, our package has something for everyone. Don't miss out on this opportunity to expand your knowledge and improve your skills. This package includes these sections: Lesson 1, Semi-Geodesic Filament Winding; Workshop 1, Simulation Automatically Semi-Geodesic Composite Pressure Vessel with Python Script; Lesson 2, Puck Failure Criterion; Workshop 2, Failure Analysis of Composite Pressure Vessel with UMAT Puck subroutine. Now let's go and watch some parts of this video package. Welcome to caeassistant.com. In this tutorial, we aim to investigate the simulation of semi-geodesic filament wound pressure vessels. In this tutorial, we will use a Python script and a UMAT subroutine in Abacus to perform the simulation. In this package, we will first introduce pressure vessels. We will also study the common materials used to make pressure vessels. Then we will discuss the methods used to construct these vessels, including the filament winding method and its various types. In the next section, we will study these vessels in more details. We will explain the semi-geodesic winding and then investigate the relationships between the winding angle and tendency to slip and the winding thickness. In the next section, we will talk about the Puck failure criterion and examine the relationships of different failure modes of this criterion. We will also briefly explain the UMAT subroutine. Finally, in the form of 2 workshops, we will teach you how to simulate these vessels practically in the Abacus software. Different materials and different uses of pressure vessels, as well as the wide range of manufacturing technologies, have led to the creation of different methods for the manufacturing of pressure vessels. One of the widely used methods of producing pressure vessels, which is used to produce fiber reinforced composite vessels, is the filament winding method. In this method, various bundles of filaments that are placed together pass through the resin bath and then wound on rotating mandrel by a carriage that moves transversely. In general, there are 3 types of filament winding patterns. The first type is polar winding, that the absolute value of winding angle is less than 25 degrees. The second is a spiral winding, where the absolute value of the winding angle is between 20 and 90 degrees. Semi-geodesic and geodesic winding are also from this type. And the third type, that the winding angle is very close to 90 degrees, is called circumferential winding. Now it is better to study the movement of filaments on the surface of the mandrel. This figure shows a small part of the mandrel surface and the geometry of the fiber's path on it. If we perform a force analysis at each point using a tangential and normal coordinate system, we will have a force vector called Fr is applied to the fiber towards the center of curvature, and the images of this force are on the tangential and normal axis. Fb and Fn, which are called oblique tangential force and normal force respectively. In this workshop, we aim to simulate semi-geodesic pressure vessels in Abacus based on the information provided. We will use a Python script for this purpose. The doom section of the vessel follows an ellipse equation, and due to the symmetry conditions, only a sector of the vessel is simulated. Now let's review the required information for the simulation. First, we need to determine the dimensions and winding specifications of the vessel. The cylindrical section has a radius of 25 mm and a length of 150 mm. The opening of the vessel has a radius of 5 mm. The ellipse diameters ratio used for the dome section is 1.2. The fiber band width is 5 mm. The helical winding thickness in the cylindrical section is 2 mm, and the hoop winding thickness in the cylindrical section is 0.1 mm. The fiber thickness is 0.1 mm and the revolve angle is 1 degree. This vessel is composed of two main composite and metallic parts. We will model the composite part using the Syllabus criterion. To use this criterion, we need the elastic properties, as well as the failed stress properties for simulation. To model the metallic region of the vessel, we only need to use the elastic modulus and Poisson's ratio. We will use 40 megapascals pressure for loading. For meshing, we consider size of 1 mm. We set the friction to 0.2 for the wet winding. With these specifications, we can simulate the vessel. However, you can modify the shape, dimensions, materials used, and other parameters according to your requirements. At the beginning of any script that is used for Abacus, there are some necessary import commands. These commands import the required Abacus modulus into the script. For example, part, material, section, optimization, and other modulus. You can see these imported modulus in this script from line 40 to 52. After that, it is necessary to receive all the data needed for the simulation from the user by means of a getInputs command. Well, our run has finished and now we can view the results. As an example, we can see the von Mises stress distribution in the part. Let's display the whole part for a better view. Use the ODB display options and in the mirror pattern tab set the settings as you see. And also remove the edges. Now we can clearly see the stress distribution in different parts of the vessel, such as the vessel door and the cylindrical part. Other outputs are also visible, such as reaction force, stress, and TSI heel damage index. The TSI woo damage index does not have much of a difference from the TSI heel. And displacement. Also, if you need other outputs, you can add them to the Python script and view them here. Let's go and check the other outputs. Here we can display different outputs versus changes in thickness. For example, we can display stress S11 for changes in thickness. But we need to select an element for this purpose. Let's select this element. This element is part of the area that we defined history output on. This plot shows the changes in S11 for changes in thickness. Here, we can also see the number of outputs. This sudden jump and big change that you see is related to the change in thickness between the cylindrical and dome parts. And due to stress concentration, we see these huge changes in S11. We can extract other plots in the same way. For example, this time we want to see the changes in the TSI heel failure index. In this plot, you see the changes in the TSI heel damage index for changes in thickness. In this plot, like the previous one, due to changes in thickness and stress concentration, we see a sudden change in the plot. In general, you can view here any output that you have specified in the script. Well, we were able to simulate pressure vessels using Python script. For better modeling of composite materials in a vessel, it is better to use an appropriate failure criterion for composites. Puck failure criterion. The Puck failure criterion is one of the most famous and best criteria for modeling failure in composite materials. This criterion can effectively identify the fracture mechanism in laminar composites. This failure criterion can identify fiber failure and damage in both tension and compression states. Also, it is capable of modeling interfiber failure in both tension and compression states. In the event of failure in the composite during analysis, this criterion provides us with new elastic and shear modulus and reducing the composite properties. To use the Puck failure criterion, we need to be familiar with its equations and formulations. First, we study the Puck failure equations for fiber failure under tension. To determine fiber failure under tension using the Puck failure criterion, equation 6 must be used. If the value of this equation is greater than or equal to 1, fiber failure under tension has occurred. This equation can be used only when sigma 1 is greater than or equal to 0. From now on, to make it easier to use, equation 6 can be called the FFT equation. Epsilon 1T is the strain under tension in the fiber direction. Epsilon 1 is the strain in the fiber direction. Then NUF12 represents the Poisson's ratio of fibers. The EF1 represents the modulus of elasticity in the fiber direction. The M sigma F is the mean stress magnification factor. And sigma 2 is the stress in the transverse direction. In workshop 2, in addition to using a Python script, we want to model the behavior of the composite material using the UMAT subroutine. The dimensions and the shape of the vessel that we want to simulate are the same as in workshop 1 and no changes are made to them. To model the composite material of the vessel using the Puck criterion and UMAT subroutine, we generally need these information. These are the inputs that the UMAT subroutine needs to use to model the Puck criterion for failure analysis. To model the metallic section, we use only the elastic modulus and Poisson's ratio as before. We will use 40 megapascals pressure for loading and consider a mesh size of 1 millimeter. And we also set the friction to 0.2 as before. With these specifications, we can simulate and analyze the vessels using the Puck failure criterion. First of all, we display the whole model in the same way as before and remove the edges of the elements. Now we can display any output that has been specified, such as a stress, reaction force. But the important outputs are SDVs. For example, SDV1 represents the value of FFT. If we check the value of SDV1, we see that it is greater than 1. So the fiber failure in tensile has occurred in the red areas. Therefore, the FFT, which is SDV6, must be equal to 1 in the red area and 0 in the other areas. This means that in these areas the fiber failure in tensile has occurred. SDV2 represents the fiber failure in compression and its values can be seen here. The maximum value is less than 1, so the DFFC, which is indicated with SDV7, must be 0 for all areas, as it is shown here. The SDV3, which represents the value of the IFFA, shows values greater than 1. So mode A of interfiber failure has occurred. Therefore, the value of SDV8 must be equal to 1 in the damage areas and 0 for the other areas. SDV4 represents mode B. We see that the maximum value is less than 1. So the failure of mode B has not occurred, and therefore SDV9 must be 0 for all areas. And finally, STV5, which represents the IFFC, has a maximum value of less than 1. So damage of mode C has not occurred either, and therefore STV10 or DIFFC must be 0 for all areas. These STVs are the failure criteria, and we can use them to determine where the damage has occurred in the vessel. Just like Workshop 1, we can display the output values versus thickness. For example, we can display the changes in S11 versus thickness. To do this, we must select the element. And we wait for the desired plot to be drawn. From here, we can display the number of outputs. Due to sudden changes in thickness and the criterion of stress concentrations, we see significant changes in the value of S11. We can display the rest of the outputs in the same way in the diagram. In general, any output that we have specified in the script can be viewed here. In this way, we simulated a pressure vessel using the UMAT subroutine.